Hey, Anna.
Hey.
What are you doing?
I'm messing with the water cycle.
Huh, how are you doing that?
Well, you see, I'm throwing these snowballs in the river, and then they melt and turn into runoff faster than they would otherwise.
Oh, all right. I guess I'll join in.
All right. The water cycle is the process through which the sun and the sun's energy causes water to change phase and move around the planet. And that's really just like heating water in a tea kettle. The source of energy from the stove causes the water from the tea kettle to change from its liquid to a gas phase, just like the sun would do on Earth. The process of phase changes from liquid to gas is called evaporation, and it's a critical piece, just like any other part of the water cycle, for our climate system and to make life on Earth viable. The thing to remember about the water cycle is the amount of water never changes. There's always the same amount of water on Earth. Water changes phases and moves around. So in one location there might be above average or below average water, just like in a drought. But the amount of water never changes. So it's critical to understand this cycle and how it plays out in the Western U.S. and what affects it to our understanding of the physical properties of water, the availability of water, and how humans have adapted. In this short video here, we'll be walking you through all the different parts of the water cycle. And for those of you who are familiar with the water cycle, we'll review how this all plays out in the Western U.S.
So we're going to use an animation produced by the National Aeronautics and Space Administration to show you how the different parts of the water cycle work. Keep in mind, this animation takes place across an imaginary landscape. We'll start off with the processes driven by the energy of the sun to turn water from its liquid form to its gaseous form. So over oceans and lakes and on the land surface where you have standing water, you have the process by which the sun's energy converts liquid water directly into water vapor, which is a gas. You also, over the land surface, have a process by which plants suck up water from the ground through their roots and transpire it directly out as water vapor through openings in their leaves. That process is called transpiration. Because water vapor is invisible, we cannot see either evaporation or transpiration as it takes place. Thus, practically speaking, we combine the two in a single term that we call evapotranspiration. Another process that's not actually described in this video, but that's critically important here in the West, and that's the process by which the sun's energy converts solid water directly into water vapor. We call that process sublimation. And sublimation is critically important in the late winter and the spring here in the West, when the snowpack converts directly into water vapor without necessarily turning into runoff available for stream flow.
So all this water vapor is building up in the atmosphere until the concentration is so high that the moisture condenses back down to tiny little droplets and accumulates in the sky as clouds. Under the right conditions, these little droplets collide and form bigger and bigger droplets that are eventually heavy enough to fall back down to the Earth's surface as precipitation. So precipitation across the western U.S. varies from a scant 2.5 inches of rainfall in the driest deserts to several hundreds of inches of snowfall in the highest mountain peaks that is stored across the winter season as a thick snowpack that eventually melts in the spring when temperatures become warmer and turns from the solid precipitation and liquid runoff. So we are very interested in that snow in these high mountain peaks, several hundred inches. That's really what makes these the moisture islands of the West. So why do we have these islands of moisture across the West? They are all located in the large mountain ranges, the Sierra Nevada mountains and the Rocky Mountains. And this is because these mountain ranges form barriers to incoming weather systems that are moving in, and then the air, including the moisture, is forced to be lifted over these barriers. The water or the moisture condenses in the air and falls as precipitation and builds these thick snowpacks.
Now let's talk about what gravity does in the water cycle. So we have a drop of precipitation that hits the land surface. Gravity is obviously going to make it move downhill or underground in any given watershed. We'll pause for a moment and explain this term watershed because you're going to hear it a lot over the next month. A watershed is any portion of the land surface where all of the water striking the land surface will go to the same channel or river. Remember this concept because it's really important. So again, we'll turn back to our drop of precipitation as it strikes the land surface. A drop of precipitation can infiltrate through the land surface and be taken up by plants through their roots. This is called soil moisture, and plants can suck it up through their roots and transpire it out as water vapor. That drop of water can also move farther underground. It can get below the point where plants can use it, and it can flow even farther underground and either flow downhill and re-enter a stream or lake farther downstream, or it can go even farther underground and enter natural reservoirs that we call aquifers. Now, a drop of water that doesn't infiltrate into the soil and move underground, but instead simply moves downhill towards a stream or a lake or another body of water is called surface runoff. Surface runoff is the most immediate way in which we get water into our stream flow and into our bodies of water. And of course, this is critically important here in the West for the water that we need in our water supplies. Finally, there's the notion of storing water in a watershed. So water that doesn't immediately move into runoff can be stored in a variety of forms over a variety of different timescales. So we can have snowpacks naturally storing water over a season. We can have a man-made reservoir storing water, or we could have one of these natural aquifers storing water over the periods of years to tens of thousands of years. Okay, so now that we've gone through the water, and the water balance is simply a mathematical representation of where all the water in a watershed goes and where all of it came from. This is really important when we're trying to understand how much water supply we have. So I'll start off with this very simple equation that's very well known in the world of hydrology. The amount of water entering a watershed should be equal to the amount of water leaving a watershed. The amount of water entering is our precipitation, which we'll represent with the letter Q. So precipitation is equal to the amount of surface runoff we have, which hydrologists represent with the letter Q, plus the amount of evapotranspiration we get, we'll say ET here, and then finally, the change in storage. So storage can either be a gain or a loss, so we'll represent that by delta S. So precipitation is equal to runoff plus evapotranspiration plus the change in storage. We can use a little bit of very simple algebra to rearrange this equation. Now the amount of surface runoff Q is equal to the amount of precipitation we get across a watershed minus the amount that we lose to evapotranspiration and, of course, our change in storage again. If you're a water manager here in the West, you can imagine that solving for Q can be critically important. That way you can know how much runoff you're going to get from a given watershed.
This is called the hydrologic partitioning equation, which really is a mathematical representation of water balance. Water balance is the concept that water is neither created or destroyed, and we can account for every drop of water within a watershed. So if we wanted to understand where all the water goes, we can look at how much precipitation fell. We can see how much evaporated within a watershed. We can look at the storage and snowpack in reservoirs or even underground, and then runoff can be measured. This all sounds, pretty straightforward, but in reality, it's actually harder to measure. So how do hydrologists measure these parameters? Precipitation, pretty straightforward, measured with rain gauges or across the West in snow measurement sites like the SNOTEL network. We have evaporation. We can measure with the parent evaporation method. Storage can be measured with a ruler in the snowpack to see how much snow there is. We can look at levels of reservoirs. Knowing what's underground is a little bit more of a mystery. And then lastly, the runoff, or Q, can be measured through stream gauges. But all of this are all point measures. We talked about stream gauges, we talked about rain gauges, and this really gives you information about how much water fell or was lost at a certain spot. What we are interested in, though, of course, is what happened at the landscape scale. And remote sensing technologies have helped us with this in more recent years, but still there's a lot of uncertainties, and these are estimates that might be, in many cases, wrong. So understanding the water balance, though it looks very straightforward here on the chalkboard, is still one of the major ongoing fields in research for hydrologists and climate scientists.
So that's a quick look at the water cycle. Thanks for joining us. See you next time.